we are good to go. Thank you for staying after the lunch. Our third, invited speaker is Professor Xiatian Zhu. He's a senior lecturer at the University of Surrey. He's with the famous group, the Center for Vision, Speech, and Signal Processing group. And he has been in this field like for a while. I mean, this multimedia and machine learning, computer vision for so many years, and we are very excited about his talk on the multimodal novel view synthesis. So let's have a kind of applause to that.
Thank you for your kind introduction, Zichuan. So yeah. Maybe I'm a new face, right? So I'm also glad to see quite a bit of face from University of Surrey and from professors, and also very exciting to be here. And thanks for the invitation to have me the opportunity to share with you the research about the multimodal learning and the 3D vision and the computer vision and this type of nature. And yeah, just a bit. Self-introduction for myself, right? So I have been in Surrey for 3-4 years, yeah. So before that, I was a research scientist at Samsung AI lab at Cambridge, right? So literally my journey a little bit complex, right? So I moved from academia to industry, then back to academia, right? So, but I enjoyed every move, right? So that's fantastic. So here actually. So I really enjoyed the last two talks, right? So the first talk is about video, right, and the 3D and everything bits, and then the second is about the creative design. And here I haven't synced with them actually, and I find out what I'm going to share with you is quite different, right? So that's good. So you can listen different topics, and maybe you can draw some different. Ideas and inspirations, right, from our talks. Yeah. So here, what I want to share is about multimodal, right? So in our daily life, right? So what is the most common modality, right? So the vision, of course, yeah. So we are from computer vision community, and everybody study image, video, or whatever, LiDAR, radar, this type of thing. And another important a bit is about audio, right? So we're talking people, and we spread our noise, right? So, and we can't live in a world only vision, right? So just like a deaf people, right? So this is, of course, we also have dedicated research about how to help deaf people here. So that's another topic, right? So here I want to share with you some research about this, and in particular also under the umbrella about generative AI. So here, this is in particular. So, how can we generate audio, yeah, over the space, right? So, suppose you have a speaker sitting there, and if you imagine you are walking around the room, and then you will listen different sound for the same sound when they transfer across the space over time, and then you will have different experience. Some places you will hear loud, some places will not that loud, right? So different directions. And the human we have 2 ears. The 2 ear actually tells us a lot of stuff, right? So when we can tell the direction, yeah, we can tell the we can tell the speed, the direction of the moving objects, for example, ambulance, right? So this is very important for us to support our decision making in daily life, right? So this is why I'm thinking this is quite a bit of general background. Okay, yeah. So this work is actually joined with Imperial College, and we have a colleague working there, and this work is published in last year New York Rips, and this is also one of the, actually, yeah, a little bit more. So I'm literally a computer vision guy, so I research a lot of image, but not really too much about audio. So just very recently, I start to move to say, well, expand my research topics to a bit more diverse, and I find out actually audio and image actually they share a lot of common things, and of course they have very different characteristics. And that is very exciting bits I want to share with you. And perhaps we have more experienced expert, right? So about audio, and if I have something which is not that deep, right? Please just correct me, okay? So let's start with the I would say very extensively studied topic, right, about the novel view synthesis, right? So this is one of the most hottest topic in the last, I would say, 3-4 years, right? So if you go to the main conference like ICCV, CVPR, you can see loads of work about how can we improve our techniques, AI, for example. How can we improve the nerve or Gaussian splatting to address some issues? So small memory footprint. Yeah, that's what we want when we use very limited resource data, for example, mobile phone. And how can we improve the modeling about the dynamic things, right? So lots of research is about static things, right? So literally the problem is like this. Suppose you are not familiar with this, yeah. So literally we have a scene here, for example, this room. Then we will take some views, right, from different positions, different angles, and this is a description about this room, right? So how can we create a virtual version about this room, right? So this is really about 3D reconstruction, right? So we want to reconstruct this physical scene, yeah, as it is, right? So, but in the digital world, so that we can actually walk through or fly through the space and time, and at different position. You have never been there, you have never captured data, but you still want the AI tell you how it looks like at that particular position and that particular direction, right? So this is all about 3D scene reconstruction. And we have a bunch of works. The nerve is literally the very first deep learning pipelines that revolutionized the current boom of research about 3D vision. And the follow-up is about 3D Gaussian splatting, right? So literally nerve is very, very expensive, right? So literally this guy is just learn. I have a mapping function I want to learn, right? So at every position and angle, I want to map this position to this kind of radiance field, right? So literally you want to tell me the color at every single point when you're looking at, yeah. So then you need to do some kind of a ray tracing, right? You kind of aggregate the information across the whole space, right? So you can imagine if you want to cast many rows, many rays, and for each ray you need to sample hundreds of times, and for each time of sampling you need to get this neural network. In general, it's a MLP kind of thing. They have tons of parameters you need to evaluate, right? So you need to do this type of thing, a bunch of things. This is very expensive, right? So then 3D Gaussian splatting is another way of modeling our 3D scene. So literally this is also a kind of volumetric representation. But instead of you using this kind of black box parameters to represent the scene, so 3D Gaussian splatting uses the explicit points, right? So every point is kind of a Gaussian distribution, yeah. So then you can use that. This is a more efficient way, because when you do rendering, you do very efficient rasterizing, yeah. So that's I think this is one of the most popular framework people have been working on, very consistent, right? But as I said, so all these things is about the visual, right? So nothing about audio, and how can we benefit the progress in visual domain to our audio, because our audio is also living in our space, right? So if the same audio, if they travel in different room with different decoration, with different audience, the travel is different, right? So this is clear. So audio's traveling is dependent on our scene. So we have advanced the scene representation. So in the another way around, we could benefit from this, right? So if we can have a better representation, then we can quantify how sound could be traveled over space and time, yeah? So then this is not easy actually if you think about that, because visual features, for example, the lighting travel, you just go straight, right? But sound is really different. Sound has very long wavelengths, right? So one example is kind of thing. If you use your hand, you can block the lights, right? So that because light is just traveling straight, right? But that would not stop the sound travel around you, right? So that's very different. So this also underpins the difference between modeling light, modeling visual data, and modeling the sound, right? So in this topic, as I said, so the task is kind of we have a speaker, suppose in the corner. Then we, instead of we capture the video, right? We have a, for example, the microphone. We can capture the audio, right? So but we want to simulate our 2 ears. Then we will capture in two dimensions, right? So one is for left and one is right. That is literally stereo, yeah, stereo, just simulate. So then we sample this type of data, and similar as visual 3D, then we want to create an AI system, right? So once we create, then we can sample literally any dimension or any directions, any positions. This is called novel view acoustic synthesis, because we are generating audio signals, but not pixels, right? So but the idea is similar, right? So how can we capture data? So literally, we also need to capture the visual geometry, visual data. So literally, in general, we will use two sensors. One is camera, another is a microphone, right? So then they comes with pair data. So at this position, this direction, we see this view, and also we have this sound information, right? So this gives us two-dimensional data, right? This is multimodal data. So this is about data structure, and after that, then we train this data. Then we want to generate at a different position. We want to say, oh, this is the left ear signal. That is right ear signal. This is the output of the generative AI, right? Okay, so this is about the task, and so this, as I said, so this extension from visual to audio is not that straightforward, right? So because of the different features with the sound, right? Sound is a very special wave. How can we do this? Yeah, this I already just discussed. So let me talk a little bit about the previous work, right? So this is actually in audio in acoustic field, right? So from a single channel input to the binaural output. This is not a new problem, right? So, but we have a new technique, so we try to level up the previous research, right? So what people have done is like this, right? So you have the input, right? So this is the input signal in one channel, right? So then the objective is very simple. You want to literally propagate this single channel over space and time and output two channels. So simulate, because you want to have 2 years experience, so you need 2 channels as output, right? People would do is kind of, oh, I develop some conditioning signals, right? So this is actually also, if we go back to the generative AI, right? So often you prompt the LLM, then your prompt is condition, right? So in this case, the condition is kind of the input audios, right? And another important condition is about the loom, right? So you need to give the information about the loom so that you can know how the sound could be bouncing around the space, right? So that is very important. And the key is really about how can we quantify more effectively, more accurate about the loom, right? Because the loom could be very, very complex. The wall, the material, the structure, the door open, some close, right? So those kind of detail all matters, yeah? So this will affect the travel trajectory of sound, yeah? So people is literally, the pipeline actually is the same here, yeah? So the key is how can we learn this type of condition, and how can we make it realistic. So literally your system can be deployed in real world. You don't need to tell every bit, because in general, we can't tell every material, for example, what is the coefficients of the bouncing for what kind of sound, for the wall, for the table. It's not possible. We can't tell. Yeah. And a little bit of research is, but the people is kind of, oh, if we can't do that, they start with some very, very simulation kind of data. We can create a very ideal room. Yeah, we tell. So they start with this and say, oh, can we learn some implicit representations for the space? So these people start with, right? So, but the idea is that you need to tell the system everything about the thing. Yeah. So where is the wall, the size, the distance, and everything. Yeah. And this is another example. Right? So literally, they want to model the bouncing between walls, right? So you have a speaker here, then you're bouncing there, and here you have a receiver, then you're bouncing back, right? So then they do this type of thing. But it's really about the scalability and the realistic issue, right? So you can't just say, oh, I want to do this, and how can you scale up, right? So if you have anything change, then the whole system will fall apart. Then you need to relearning from scratch. Yeah, that's not what we want, right? And the reason that people say, oh, okay, can we just use photos, right? So photo is easy to take, right? So we just boom, take 3 images, then tell, oh, this is what you have, right? So this is people traveled, and this is what we are traveling to, right? So, but we are going more further, right? So just as I said, if I'm the listener, I'm standing here, I'm facing there, I see this view, right? But the sound is just go all around, right? So it's not only the view you see will affect the listening, but the whole thing. So that's the idea behind we say, how can we quantify the holistic, the whole thing, so that we can better condition the generation process. That's the whole idea, right? Okay, so still we follow the recipe. So literally we want to say, oh, how can we literally put everything in the conditioning? Yeah, but the key point is that how can we draw the information around the whole thing? Yeah, not only the view the listener is seeing. Yeah. Then back to the 3D Gaussian spreading, right? So literally 3D Gaussian spreading already capture us a very coarse kind of material information, right? So as I said, and this could give us some starting points. So for example, this is wall, this is table, and this could give some information, but that is not enough. Yeah. How can we do this? What we do is here. So literally, we find out actually the key point is we of course we start with 3D Gaussian spreading, right? So but when we apply to audio, we find out actually Gaussian spreading has the problem with because the focus is about the to draw rendering the pixels, right? So the focus is kind of you have a lot of points to describe the edges, right? And you just need a little bit points to describe, for example, this kind of very flat, very big areas. You just need a little bit of points because that is discriminative enough to describe this surface. But for edge, you need more points. But the key is that for sound, actually, what matters for sound is kind of the surface actually matters more than the edges, right? So you can imagine if the sound hit on the wall, then will bounce off the wall, right? So that bit actually is more important for sound. So this bit is one of the key difference between sound, audio, and visual. So we need to do something different, yeah? And also beyond that, and for visual type of points, so they have no kind of acoustic properties, right? So how can we, for example, enhance 3D Gaussian points with this type of information? Then how should we do that? Yeah. So I just quickly jump this. So we started with the standard Gaussian splitting, and we just learn, for example, because we don't need to get very fine-grained details, so we can literally half learn maybe if the standard learning process need you 10,000, we just 5,000, that would be okay, yeah. And then, based on that, we say, oh, for each Gaussian point, we want to learn something which represents the sound propagation features, right? So in this case, we actually we propose something called acoustic feature vector. So this is initialized from the visual features, for example, the color, for example, the opacity, right? So that tells us some information about the material, some about except the location, right? So, but we share the location because this representation is still about the same, so we can still share the same location here, right? Okay, then we have actually, this is our pipeline here, right? So first we train a standard 3D Gaussian splitting. Then the second step, we say we want to introduce some audio related information for every single point, for every single Gaussian point, right? So that is initialized by the appearance of the information. But the key bit is that after that, the 3D Gaussian bits will be totally frozen. Then we use the acoustic information because we already have the training data, right? So we have the single input and two-dimensional output. That is the observed or the seen acoustic information. And we use that to back propagate. This is literally the standard learning process, right? So we want to really optimize the acoustic guidance feature vector so that can actually implicitly learn how sound can bouncing around in the space. Yeah, so that's actually it's the main bit. Yeah, so I quickly jump in, quickly go skip those details, and so you can see for initialization we have this alpha. Alpha is literally tied with every single point here, and this can be optimized with the opacity and the SH. And this, because this is a vector, right? So literally is a very, just like you mapping an image to latent vectors. Here is a dedicated audio specific vector, right? So it's hard to explain, right? So everything is just some numbers, right? So it's difficult to interpret. It's kind of black box, yeah. Then stage 2, we say we do this, we forward this, and the whole, the X, Y, Z, and this location of each point will be finalized by then, and then we will dedicate it to learn this audio-focused latent embedding, right? So then the third step is just how can we optimize with the standard rendering errors, right? Rendering propagations. And you can see here, actually, I just want to visualize a bit, right? So here we have, this is a loom geometry, this is a Gaussian points here, right? So we have the speaker here, and we have the listener here, right? So you can see, and I use different color to visualize the contribution of each point for this sound backpropagation between the speaker and the listener, right? So, for example, you can see, oh, this kind of area, the points actually contribute to more actually for this for the listening, yeah, what sound the listener can receive, right? So, and if you increase the distance between and you change the location, then you can see the different points will have different. And for this type of points, you will receive very little impact, right? So kind of, this is a kind of a loom with, if I remember correctly, this is a kitchen, this is another bedroom, that you can see this type of thing has non-effect on the sound propagation here. And if we expand to even further, right? So you can see the distribution of the sound contribution to the listener's signal, right? Yeah. What's going on? Time. How much time? Okay. Thanks for the reminder. Okay. Yeah. Maybe I will stop earlier. But anyway, so the now here is also, we compare with another method. Yeah, actually is also published just before us, right? So they are based on NERV, and we based on the Gaussian splitting models, which is more efficient. And you can see the signal here. This is the ground truth, right? So, and this is what they get, and we got much closer signal shapes here. Yeah. So and I show here, and this is another examples, and I will show you some other example. And because as I said, the sound actually tells us the directions, right? So we can see if the distance between listener and the speaker is increasing, right? So if increasing, then you can see the magnitude will gradually dropping, right? So this will give you some information about the distance, yeah. So the distance between the 2 points, yeah. So that's also very important for sound perception, and also this is directional, right? So if the listener standing on the left side, then you can see the left side will much louder signal received, and in the opposite side, then you will see the right side will be, yeah. So this will tell you the very important information, direction, distance, and everything, yeah. So this is very. Actually, I want to share the very recent work, because as I said, this vector tied with every single point is hard to explain, yeah. So, and what can we do? What can we make this model more transparent? Actually, I'll quickly just share a recent work. What we do is that actually we further introduce some. I just go to the model. We have so literally we introduce a very explicit sound propagation model, right? So it has 3 stages, right? So for example, given the sound, we say for every we have 3 stages. The first stage is kind of we spread some energy at the beginning from every point. And then the sound will bouncing between points, right? So that will give us some kind of, the energy is kind of diminishing, right? So this is, and the third stage is called, this is called self-transferring. This is kind of, you consider bouncing. And then the third point is kind of actually specific points. Then you will receive information, receive the signal, and those signals is literally is drawn from all kinds of different points, right? So you need to have some aggregation. So you have a 3 stage to very explicitly to model the process, so that make the AI is more transparent and also more physically aligned. Yeah. So I think physically aligned is very important in many ways. And actually, one of the thinking I have a long time thinking about why multimodal large language model, they can't do many things, and they need to just get so many data to be trained. Yeah, tons of data, tons of GPU hours, and tons of efforts. Right? So why they need so much data to understanding this, but they still can't grasp the, for example, the physical laws behind the data, right? For example, why the water is flowing from top to down, this type of thing, right? So I would say there is a very fundamental missing mechanism behind that, because how can we pick up those physical laws, which literally is the driving force behind our data's observation, right? So I think this work is the kind of, we want to do a little bit work towards that step, right? So this is maybe in the future, I would say this is one of the, we have a big word called physical AI, right? Physical AI is something we are doing this. We want to make the learning more efficient, but also more consistent in terms of the understanding about our world, right? So I think I just stop here. Okay. Yeah. Okay. Thank you very much.
Question 5.
Yeah.
Hi, thanks. Wonderful talk. I was wondering about the data set you used for gathering the acoustics, because I guess we didn't talk much about that, but it seems like there's quite a lot you could have fit on.
You can find some standard data benchmarks, yeah, online, yeah.
And for training?
I believe more and more is coming up. Yeah, some from Facebook, Meta, some kind of. So this is a kind of one research behind the AR, VR. Yeah. So virtual reality, right? So.
Okay, and I guess my other question is about the material awareness.
Yeah.
How do you encode that?
So this is all learned from data. So as I said, so literally in this, because no magic, right? In general, we start with visual data, and then you say, oh, can you tell me the coefficients of material? I will say it's super hard, right? But what we want to emphasize here is that how we are focused on how the sound travel, because I just assume this is what you're given, right? So I have no idea. I just say some properties with the material, but under this condition, how the sound propagates. So this is the key of the learning, right? So, but if we say, can we recover the material properties now? This method still can't do that, yeah. But that's a very good question. This is a future research. You can be part of that.
Okay, thank you, sure.
A quick question. When you capture video plus image, I'm wondering if you need to pause the camera and capture a few seconds of audio, because the audio signal in a particular location, you just have an instantaneous response. Do you need to average it in a time period when you move the camera in different location?
But here, I think mostly you are talking about the more maybe dynamic things, right? So dynamic things, maybe the audio is kind of different, but that's another thing. So here, what we studied here is mostly about static, yeah. So the frame literally is still over time, yeah. So we don't need to average, yeah. That's a good point, absolutely.
Hiya, love the talk. I wanted to ask about the data gathering for the audio, right?
Yeah.
Because you stated that you use left and right audios, like microphones, I'm guessing, right? Does the audio data gathered account for the shape of, like, the biology of human ears and the shape of human ears and how that affects reception of the sound and how the sound would be received by the microphone, right? For example, because like human ears are slanted forward slightly, right? And like that would affect how a microphone would receive that sound, and whether or not that really matters in the grand scheme of it.
That's absolutely great details. Yeah, to be honest, we don't contribute to the data creation, but from my remember so what is the collect data is kind of so if you say you want to consider the ear shape, the direction, so we can have this type of avatar. That's fine. So we just use some avatar to simulate a real person, and then you have.
Would that translate to an accurate representation of a human listening experience, even if the data is like flat?
It should be very close. That bit I don't think there is very much scientific challenge there. It's really about how you want to craft your data collection process, right?
Yeah, no, that makes sense.
Yeah, thanks.
Before I
yeah, it's okay. Should be.
Before I ask question, I would like to give one more comment on the ear issues, because I previously worked on audio research, but I'm not that familiar with 3D. And if you want to add the ear phenomenon, then you typically add some transformation function called HRTF or something similar to consider how the human facial shape and how the ear shape and how the delay between the left ear and right ear will affect your signal that is received by your ear. So it may add one more transformation function for the signal. So, and back to my question about your research. First, I would like to confirm if I understand correctly. Are you trying to modeling the impulse response of the point in each point of the space? I mean,
responsible. You mean you're talking about the RIR, right?
Yeah.
Right? So for this work, it's not about that. We directly generate the sound, not about the responding. But I think RRI is more. I would say it's a more general representation. That could be, yeah.
So
we have
your input is arbitrary audio, and your output is how the audio can be listened in an arbitrary point inside the room.
Yeah, absolutely. Yeah,
okay, so
right.
Then from a signal processing perspective view, you are modeling the function H, which is called impulse response. Then every input signal X will be transformed.
Yeah, I think the principle is the same. That's the principle, but just different representation, I would say.
Okay. Yeah. And my question, I have another question. Sorry. And what is the evaluation metrics you have? Because if you, for example, calculate the L2 norm or something like that, or
no, we just use the standard audio metrics. For example, the elopes kind of thing.
I mean, there are a bunch of metrics.
Yeah, we will batch a bunch of metrics.
Okay,
I can't remember actually the names.
Right.
Yeah, so this is the standard bits. We don't introduce anything new. Yeah,
okay,
for there.
Thank
you. Thank you.
Thank you. Right out bit. So let's give a round of applause to